Good morning, dear students. Welcome to Pundachandra Higher Secondary School. Okay, so in the previous class we have completed our chapter number 3, that is electric current. Okay, we have, with all respect, we have completed these three. Then next we are moving into the chapter number 4, that is the magnetostatics. Okay, actually the whole chapter number 4, chapter number 5. Okay, and chapter number 6, basically these three includes under your magnetostatics. Clear? So in the first part of your magnetostatic, that is your chapter number 4, that is magnetic effect of electric current. So as the chapter indicates, heading indicates magnetic effect of current. Let us discuss about these things. How the current gives a magnetic effect. So in 1820, okay, in 1820, a Danish physicist Ørsted performed an experiment. So let us discuss the experiment very shortly. It's a very interesting experiment. So what he did, he took two circuits, actually two electrical circuits. AB is the current conducting wire, AB is the conductor. Look at it, AB is the conductor. Okay, and the AB conductor is connected to a battery. This is the battery. Okay, and the in between the conductor and the battery there is a switch or key. Okay, so in the first circuit, all of you can see the key is open. The key is open, but in this part the key is closed. Understood? So look at here. When the key is open, that means there is no current flowing in the circuit. So there is no current flowing in this because the key is open. But here the key is closed. So that's why the current is flowing in this direction. Look at it. This is the direction of current I. Okay. So now next what he did? Now he just placed. Look at here. He just placed a magnetic needle. So this is your magnetic needle. He just placed a magnetic needle. Okay. So what he observed? He observed that when the magnetic needle is placed here. Okay, when the magnetic needle is placed near the conductor, in the case number 1, this is the case number 1, as there is no current flowing in this circuit, that's why there is no deflection in this magnetic needle. So this is your magnetic needle. Okay, and as there is no current flowing in this circuit, so there is no deflection in the first. But come to here, he observed that where there is a flow of current, there is a flow of current here. Understood? Okay, so now there is a deflection. There is a deflection in the magnetic needle. This is the deflection. Look at it, there is no deflection, but here there is a deflection in the magnetic needle. Okay, so this is your deflection in the magnetic needle. Clear, all of you? So now he conclude that from this experiment, he conclude that there is in this part there is no current flow, there is no deflection. But in this case there is current flow. Okay, and there is a deflection in the magnetic needle. So he concluded that there is a magnetic field associated with this current carrying conductor. The conclusion is very important, listen very carefully. Ørsted concluded that, the physicist Ørsted concluded that there must be a magnetic field associated with this current carrying conductor AB. Okay, there is a field, that field is called as magnetic field. Clear, all of you? Okay. So now, due to that magnetic field, the magnetic needle deflect. Very simple. Clear? So this is the conclusion. That means we can call a line that due to the flow of current in a conductor, around the conductor a field is generated or a field is produced. That field is nothing but your magnetic field. Clear? So this is some discussion about the Ørsted experiment, and from this it is observed by the Ørsted that due to the current flow there is a field generated around the conductor, and that field is called as a magnetic field. Clear? Okay. So now from this experiment, let us now see, suppose we are taking a infinite current carrying conductor. Let us take, so this is, look at here, this is a plain sheet. All of you look at very carefully. So this is, let us take a plain paper, okay, and on the plain paper I will put a hole, or I will make a hole, and through this hole there is a infinite current carrying conductor placed in this manner, clear, and in this conductor there is a flow of current, I. So that means this conductor is a current carrying conductor, very simple, okay, and there are some your iron fillings, but dust of irons are present on it. Let us put some dust of irons or iron fillings on this sheet. This is your paper sheet. This is your paper sheet. So when we connect this conductor to a battery, listen very carefully, when this your conductor is connected to a battery or a voltage supply, then what happens, there is a field generated around it, and it can be observed that the iron fillings present over the sheet, the iron fillings, small iron particles which we have put on it, they make a concentric circles like structure. Okay, listen very carefully. That means these iron fillings are make a concentric circles. Why? Now due to the effect of magnetic field. Due to the effect of magnetic field, the iron fillings make a concentric circle. Clear? Okay. So now, what is the direction of magnetic field? Let us see. So this direction of magnetic field we can find out with the help of Maxwell's right hand thumb rule. Very simple. Okay, or Maxwell's screw rule. Okay, so now that means, suppose this is my right hand. Look at, this is my right hand. I will place in this manner this thumb. Okay, this thumb gives the direction of current. Okay, and the curling finger gives the direction of magnetic field. So this is the direction of current. This is the direction of current. So that means I will place it in this manner. Now look at it. The curling finger is in this manner. Very simple. The curling finger in this manner. That means the magnetic field is in this direction. Clear all of you? Okay. So now this is the direction. Suppose I will make some change and I will reverse the direction of current. Then what happens? Look at very carefully. The same thing I will do. Okay, and I will put some iron fillings. So when the current is passing, but here the current becomes upward. Okay, or you can call it the current is flowing in anti-clockwise direction. But here look at here, the current is downward or it is flowing in clockwise direction. So in this, the iron fillings also make a concentric circles. But if we will apply the thumb rule or Maxwell's screw rule, listen very carefully. So according to the Maxwell's thumb rule, or screw rule, so we will place it in this manner. Okay, this is the direction. Look at here very carefully. This is the direction of current, and this is the direction of magnetic field. So the current is expressed with the magnetic field in this direction. So this is the direction of your magnetic field. Clear all of you? Look at these two figures. Understood all of you? Okay. So now that means we can conclude that if the direction of current is reversed, then the direction of magnetic field is also reversed. Understood all of you? So this is the pattern, or this is the nature of this magnetic field when the current is passing through a straight conductor. Clear all of you? So when the current is flowing upward direction, the magnetic field is in this manner. When the current is flowing in downward direction, or this is clockwise or this is anti-clockwise. Okay, either or you can remember. This is the pattern of your magnetic field. Clear? All of you clear? So this is the effect of current carrying conductor on this magnetic field. Understood? All of you understood? So now, from this, we can take a very little bit summary. What you can take a summary? Now we can take a summary just like that. That when a conductor, okay, where a conductor is connected to a source, a current is flowing through it. Due to the current flowing conductor, okay, if or not if actually the magnetic field will deflect. Okay, why the magnetic field deflect? The magnetic field will deflect due to a field around or associated with this conductor. That field is called your magnetic field. Clear? And another very important concept is there. So why the actual magnetic field generated? Let us discuss somehow. Okay, so now the magnetic field is generated due to magnetic force. Listen very carefully. Okay, so magnetic force means, that means in the, let us revise something. In the electrostatic, what happens? We deal with static charges. The charges are not moving. We are not dealing with the moving charges. But in case of your magnetic field or magnetostatic, we are dealing with the moving charge. The charge are flowing. They are not static. Okay? As the charge flows, the current generates. Very simple. Clear? And due to that flow of current, a field is generated. Because suppose we are taking a magnetic field. So this is suppose a magnetic field. Okay? We are taking the magnetic field as B. Let me take the magnetic field as B. And look at here. Here the magnetic field is uniform because the magnetic field lines are parallel. We have later on we have discussed about what is magnetic field lines, so don't worry about that one. So as we know that the electric field lines are, if they are parallel, then the electric field is uniform. Similarly, these are the magnetic field lines. So if the magnetic field lines are parallel, then this is a uniform magnetic field. So now in this magnetic field, suppose a charge, we will place a charge on it, or we will move a charge on it. Suppose we will take a charge Q, okay, and the charge is moving with a velocity V. So again I will repeat. So this is a magnetic field. What type of magnetic field? Uniform magnetic field. Let us take B. So in this magnetic field I will place a charge Q which is moving with a velocity B. Okay. So now this, from this discussion, what we are going to find out? Now we are going to find out what is the force actually applied on this charge. And due to this, okay, so what is the force? The force F, this is due to the magnetic field. Let us name it as FB. Okay, very simple. So FB is equal to, the expression is that Q whole into V cross B. Okay, this is the amount of force. This is the amount of force, okay, applied or on this charge Q when the charge Q is placed in a magnetic field. Clear? And that type of force is having a very specific name, important, that is called low range force. Low range force, remember? Okay, that is the low range force in magnetic field. Understood all of you? And that is the amount, again I will repeat, that is the amount of force applied on where? On the charge. When the charge is placed in a magnetic field, okay, and the charge is moving with a velocity V, okay, and that expression of Lorentz force at B is equal to Q1 into V cross B. That is very important. That means from the problem point of view, so FB is equal to QVB in sin theta. So this is the expression. Because V cross B is nothing but your VB sin theta, we know that. Okay. So this is your Lorentz force. So due to that Lorentz force, okay, the magnetic field is produced. Okay. So the current, this is the, actually we have discussed now how the current, due to that flow of current, the magnetic field generated. Okay, so in that, where the magnetic field is generated, there must be presence of magnetic force, and that magnetic force is called Lorentz force. Understood all of you? Clear? Okay. So now, with this discussion of Lorentz force, it's a very important one. Listen very carefully. The Lorentz force is very important. F is equal to Q1 into V cross B. Okay. So now with this discussion, let us go to another important part, that is your Biot-Savart's law. Biot-Savart's law. Okay, that law is a very important law in this chapter. Okay, so what the law or what is the aim of this law? First we will discuss this law. Okay, with this law we can find out what are the factors upon which the magnetic field due to a current carrying conductor depend. Remember, okay, again I will repeat, Biot-Savart's are two scientists. Biot is a scientist, Savart is a scientist. So Biot and Savart, they performed an experiment and they conclude or they observe what are the factors, okay, what are the factors that will affect the magnetic field due to a current carrying conductor. Clear? So let us now verify the law. So what the law states that? So before that, let us suppose this is a conductor. Suppose this is a conductor I will take. Okay, the conductor, this is infinite conductor. Let us take it as this is the x, y. Okay, so what is our aim in this law? So this is, suppose at this point I want to find out. So this is, very carefully, this is the point P. Okay, so now and this is R, this is your DL, the current flowing is I. Okay. Clear? So now, so this is the figure. Look, before discussing or going into the Biot-Savart's law, let us discuss about this figure. So I will take a current carrying conductor first of all. The conductor is XY, this is infinite conductor, but let us take it is XY, the conductor name is XY. And in this conductor, it is infinite conductor, so we will take a very small element DL. Again I will repeat, we cannot find out the whole length of the conductor, so that's why we will take a very small element DL. DL is the small element belonging to this conductor XY. Okay, and as the XY conductor carrying a current I, so there is also I amount of current also flow in the small element DL. Okay, so what is the element? So that element is current carrying element. Current carrying element is how much? Ideal. The element is ideal as the DL conducts a current I. That's why the current carrying element is your ideal. Okay, so what we are going to find out? Now we are going to find out the magnetic field at the point P. Okay, we are going to find out the magnetic field at the point P due to this conductor, current carrying conductor. Okay, so we cannot find out the whole conductor. That's why we will take a small element here. Very simple. This is the direction at which we will find out the magnetic field. Clear? So now this law, the Biot-Savart's law states that the magnetic field dB, okay, the magnetic field dB at the point P, listen very carefully, Biot-Savart's law states that the magnetic field at any point P, okay, is directly proportional to the current flowing through the element. The current flowing through the element. So what is the current flowing through the element? I. Okay. Then the magnetic field directly proportional to the length of the element, that is dl. Okay. Again, the magnetic field is proportional to the sine of the angle. The sine of the angle between the dl and the r. Again I will repeat. dB proportional to the sine of the angle between the element dl and the distance r, or the distance vector r. So what is the angle? Theta. So that's why sin theta. Clear? Now, next. And inversely proportional to the square of the distance between these two. The square of the distance between the element and the point P, that is r square. The distance vector is r vector, so the mode is the distance, so the distance is r square. So let us combine this. Now that implies what I can write? Now dB is proportional to I dl sin theta divided by r square. Okay, so according to Biot-Savart's law, again I will repeat, the dB proportional to the current flowing through the conductor, the magnetic field dB proportional to the length of the conductor, the length of the element dl. The dB is proportional to sine of the angle between the dl and r, and dB is inversely proportional to the square of the distance between dl and point P. Okay, so dB proportional to ideal sin theta by r square. That implies dB is equal to a proportionality constant k I dl sin theta divided by r square. Okay, so that implies dB is equal to, so that proportionality constant k, value is mu 0 divided by 4 pi. Remember, the proportionality constant k value is mu 0 divided by 4 pi. So let us put the value here. So mu 0 divided by 4 pi I dl sin theta divided by r square. So this is the final expression of your Biot-Savart's law, but this is in which form? This is in scalar form. Okay, so dB is equal to mu 0 by 4 pi dl sin theta by r square, where this mu 0 is equal to permeability in the free space. Okay, in the electrostatic we are dealing with epsilon 0. Epsilon 0 is the permittivity in the free space, whereas mu 0 is the permeability in the free space. So mu 0 is again the property of a medium. Which type of medium? The magnetic field. Where we are dealing with magnetic field. But epsilon 0, which we have discussed in the electrostatic, that we deal with the electric field. Clear? So mu 0 is the permeability in the free space. The value of mu 0 is equal to 4 pi into 10 to the power minus 7, that is Tesla meter per ampere. Okay, so mu 0, the value, remember the value is mu 0 is equal to 4 pi into 10 to the power minus 7 Tesla meter per ampere. Clear, all of you? Okay, so that is now, this is the scalar form. If we will mention the vector form, then look at the vector form. So what is the vector form? The vector form is dB is equal to mu 0 divided by 4 pi I dl sin theta divided by r square r cap. R cap is nothing but the direction. Here we have to find out the magnetic field. Due to this, again I will repeat, we have to find out the magnetic field at this point. Due to this, that's why the direction is in this direction. The direction is in this direction. Okay, so if now we will apply the right hand thumb rule. Apply the right hand thumb rule. So in this conductor, this is the direction of flow. So look at here. Look at here. So now, if this is the flow of current, and the curling finger gives the direction of magnetic field. So what type of magnetic field we are dealing with here? Inward. Okay, this is the diagonal repeat. This is the inward. All of you look at it. Okay, so this is my right hand. This is my flow of current. This is my flow of current. Okay, upward. And this curling finger gives the direction of magnetic field. Okay, so this means this cross. This cross means inward. Okay, the direction of magnetic field. So this is nothing but your r cap. So that implies dB is equal to mu 0 divided by 4 pi ITL sin theta. If I replace the value of r cap, what I can write? Now r vector divided by r vector magnitude. So this is r square. That means r square into r square how much? Sorry, r square into r how much? R cube. So now this equation number 1, this is equation number 2. Okay, so equation 1 is the scalar form of Biot-Savart's law. Equation number 2 is the vector form your Biot-Savart's law, and the direction of, again I'll repeat, the direction of magnetic field. Okay, the direction of this magnetic field we will find out using the Maxwell's right hand thumb rule or Maxwell's screw rule. Very simple, the screw rule and Maxwell's thumb rule. If you will apply the screw rule, then all of you have observed the screw. Any screw will take a screw. If we will rotate the screw, in magnetic field direction, or if we will move the screw, the pin of the screw in the direction of current, then the rotation of the screw give the direction of magnetic field. Very simple. Okay, that means suppose I apply here. Now the current is upward. The current is upward. Okay, so now if the current is upward, then the screw, I will place the pin of the screw in this direction. I will rotate it. When I will rotate it, we will observe that the magnetic field is inward. Very simple. Okay, so now this is my discussion about the Biot-Savart's law. Okay, so Biot-Savart's is very, very important as per the exam and also from the problem point of view. So this is my scalar form and this is my vector form. Clear enough, dear students? In the next class, we will discuss about the application of Biot-Savart's law. This is also important and this is a long question. Okay, so now so this is a very important part. Let us go through my notes. Okay, thank you. Have a